I'm Bill Grob, Director of the National Center for Supercomputing Applications at the University of Illinois and Vice Chair of SC20 Invited Talks. Welcome to the SC20 Invited Talk session on post-Moore's Law devices. The overarching theme of SC20 is more than HPC. Complementing this theme, the Invited Talks collectively focus on applications and technologies impacting all areas of science, engineering, medicine, and society. Our community is at the crossroads as we keep getting reminded of slowdown and end of the Moore's Law. The distinguished speakers in this session will provide insights into ongoing research and development of post-Moore's Law devices. Shekhar Borkar is Senior Director of Technology at Qualcomm Incorporated, a retired Intel Fellow and an IEEE Fellow. He worked on the 8051 family of microcontrollers, supercomputers, high-performance and low-power digital circuits research, and served as the principal investigator of several DARPA and DOE-funded projects. Shekhar was an adjunct faculty at Oregon Graduate Institute and taught graduate courses on VLSI design for more than 10 years. His research interests are low-power, high-performance digital circuits, high-speed signaling, and system-level optimization.
The title of my talk is Future of Computing in the So-Called Post-Moore's Law Era. The reason I call it so-called is because I don't think that the Moore's Law is over yet or will be over in the near future. And that's what I'm going to explain in this talk. So here's the outline of my presentation. First, I'm going to show you the technology scaling and the Moore's Law as we interpret it. Then a roadmap, a long term, a medium term, and a short term, followed by some of the new emerging devices, where they stand, potential solutions for medium term to keep Moore's Law going, and how we can reclaim efficiency in the short term to keep the Moore's Law going. Finally, I will describe relevance to the HPC world, and then I'll summarize my talk. What this slide shows is the 50 years of technology scaling, and this is data for 48 years of microprocessor trend data that's been collected by Professor Horowitz at Stanford and recently also updated by Carl Krupp. And what this shows on the x-axis is the year of introduction of a processor, and the y-axis you have transistor counts in thousands, performance, frequency, power consumption, as well as the number of cores that have been employed in the processors. If you look at the trend, first notice the power. The power started increasing, and then just about 20 years ago we hit what we call the power wall. Along with that, if you look at the frequency at the same time also leveled off. Then to improve the performance, we decided to increase the number of cores, and that was an era of multi-cores. And with multi-cores, what happened was that the throughput performance went up, even though the single thread performance too went up a little bit. And then finally, if you look at the transistor integration capacity continued to approximately double every 2 years, what was originally interpreted as Moore's Law. So what did we do with the transistors? In the early years, the transistors were used for logic, and the logic transistors dominated. Then in the middle, there were 50% logic and approximately 50% memory. And in the last couple of decades, most of the transistors were really used for the memories, especially the caches on the processor. Now let's look at the interpretation of Moore's Law over these years. In the first couple of decades, the Moore's Law was interpreted as doubling the transistors every 2 years. Then it was interpreted as doubling the frequency every 2 years, especially in the 90s when the Dennard scaling was at its peak. When the Dennard scaling started going down a little bit, we redefined Moore's Law and we started calling it twice the performance every 2 years. The question is, in the coming decades, what is the interpretation of the Moore's Law? And that's something that we'll talk about at the end, having seen the entire landscape. First, let's ask the question, why did the frequency level? So what I'm going to go through is a series of description about the transistor. So let's take the transistor, and this is the voltage across the transistor. And this is the current on a log scale through the transistor. So when the transistor is turned on, it's got an on current, and as you reduce the voltage, the current through the transistor starts decreasing exponentially as shown on this diagram. Now this is what we call the threshold voltage. That means this is the voltage at which the transistor starts turning on. That's the threshold voltage. Now this is what we call the off current or the leakage current. That means when the transistor as a switch, when it's turned off, it's still leaking, and that leakage current is the one what we call the leakage power. Now as you start scaling the voltage to reduce the power, you can see that this graph shifts to the left, and when it shifts to the left, the off current or the leakage current increases, and since this is a log scale, that increase is exponential. So you get an exponential increase in leakage as you reduce the supply voltage. Now let's look at the implications of that on the different technology generations. So processors on, for example, 1 micron technology, the leakage power was in microwatts. Now every generation you double the number of transistors and the exponential leakage increases, the leakage increases exponentially. As a result, somewhere around 0.35 micron technology, you had milliwatts of leakage power. Then it became watts on 180 nanometer technology. At this rate, it could have gone to hundreds of watts, but we really didn't want hundreds of watts. So what we did is the supply voltage scaling, as you can see here, started to level off. So as you level off the supply voltage, what happens to the frequency? And that's shown here in a simple formula. Frequency is 1 over T, which is the current I divided by CV, where C is the capacitance and V is the supply voltage. The current I scales to 0.7 because you have a 30% reduction in the size of a transistor. The capacitor also reduces by 0.7, but the supply voltage V, which is 1, which stays at 1, and as a result your frequency is also 1. So your frequency levels off. Now there is a way to still increase the frequency, and there are two things you can do. One is increase the current I to provide the higher frequency. Second thing that you can do is you make the subthreshold slope steeper. That means if you look at the slope of that green line, if you make it steeper, it allows for a lower supply voltage of operation. So with this in mind, there was several advances in the CMOS. The first notable one is what you call strain and stress. What this shows on the left hand side is the NMOS transistor, and these are the source and drains, and you apply strain onto the source and drain. Similarly, on the PMOS transistor, you apply stress on source and drains. So applying strain gives you the improved mobility. With improved mobility, you get the higher drive current. This was first time done on a 90 nanometer CMOS by Intel in 2003. The second significant advance, as you see here, is the high K, which is the high K dielectric material for the gate, and the metal gate. What this does is it enhances the drive current of the transistor. It was first demonstrated somewhere around mid-90s, around 1995, but it really happened in products in the 45 nanometer technology by around 2007. And the third advance that I want to highlight is the FinFET, or what Intel calls the tri-gate, and that's shown over here. And what you see here are these fins, and this is the source and drain that you see into it, and there is a gate dielectric. And this fin, having the gate all around it, has a much better or a much steeper subthreshold slope. So a steeper subthreshold slope gives you two things. It gives you lower voltage of operation and enhanced drive current. This was first demonstrated in 1999 and then went into production on 22 nanometer by Intel in 2012. One thing to notice from all this, it took about 10 plus years to mature a new technology. And as far as I see them, there are no new major advances in sight today. Well, with this, here's a proposed roadmap that I would like to propose. Number one, in the longer term, 10 to 20 years, we must look for new devices to replace CMOS. And along with that comes the circuits, the architecture that goes with it, and the system level research to use these new devices. Second thing that you can do in the medium term, which is 5 to 10 years, is enhance CMOS and apply system level innovations. And also, let's not forget about the circuits, the architecture, and the systems research that goes along with it. Third is the short term, in 1 to 5 years. In 1 to 5 years, CMOS is it. So what we can do is let's go and reclaim efficiency by overhauling circuits, overhauling architectures, and essentially looking at the system alternatives for efficiency. So this is my proposal of 3-step roadmap. Let's look at the long term. What are there for the CMOS replacement in the long term? There is a lot of research that's been going on in the universities as well as in the industry that's been funded. Fundamentally, there are two types of devices that people are looking for: charge base and non-charge base. And even in the charge base, you're looking at thermionic and non-thermionic. Non-thermionic are things like the tunneling transistor, and the thermionics are the field effect transistors as we know today in CMOS. So what you see here is you can see there are spin devices, there are carbon nanotubes, there is a graphene, there are all kinds of devices that are in the research. Research continues, but there is no winner in sight yet. That doesn't mean that we should give up. We should continue the research, and when it's ready, we should use it. So here is a good paper that's at the bottom that's been shown over here, and this shows the new devices in research, especially evaluated with a 32-bit adder. So this is a 32-bit adder evaluated. On the y-axis, what you have is the energy in femtojoules on a log scale, and on the x-axis, what you have is the delay in picoseconds and also on a log scale. So these slant lines are the constant energy delay product lines, because you have always trade-off energy versus delay. Notice one thing. Today's CMOS high performance HP shown in green over here, and CMOS low voltage shown in green over here. They lie somewhere here on this graph. All the other devices near it, shown in blue, they are our field effect transistors. Now mind you, lower the energy is better, lower the delay is better. That means as you go towards the origin of this graph, the better off you are. Now look at all the blue devices that are in research, or the charge-based devices. They are closely clustered with our present day CMOS. All the other futuristic devices that are shown over here, such as the ferroelectrics, the spin torque, the magnetoelectric, and so on, they are far away. That means they are not there yet to compete with CMOS. Lot of potential, lot of research needs to be done, but these devices are not yet ready for mainstream. So what are we going to do in the medium term, which is 5 to 10 years? So what I'm going to show you is an example. This is just an example to get the creative juices flowing, and this is inspired by research on Josephson junctions. Now mind you, I'm not endorsing or promoting Josephson junctions, but just looking at the research that's been done on Josephson junctions, here are some observations. First, there's a low energy of Josephson junction because of low voltage swings. And low voltage swings means energy which is a quadratic with voltage is lower. Now this is made possible by low temperature. In case of Josephson junctions, they are cryogenic temperatures. How do the circuits work? Because the noise floor is very low, and as a result there is an adequate signal to noise ratio. Now they also have superconductivity in there, which helps the frequency but not really the energy. As a result, the overall energy is reduced because of the lower supply voltage and the lower swings of the signals. The energy is reduced despite the energy it takes to cool it down to cryogenic temperatures. At least that's the claim. So my rebuttal is if these claims are true, why not engineer CMOS for low temperature, and that should also provide the same benefits? Again, this is an example. This doesn't necessarily mean that this will happen, but something to look at. So, and if this is possible, then here's a spectrum of temperature. We are at room temperature. We could start thinking about operating CMOS at 0 degrees Celsius, which is 273 Kelvin, or dry ice for that matter, or you can cool it down even further to liquid nitrogen. And if you are really brave, go down to the cryogenic temperatures. So I said, let's go and do some study as to, is it possible, can this be done? And this is some of the research that was funded partly by DARPA and by the JUMP program, and I'm going to show you some of the results that were obtained at the universities. So first, how do we do this? How do we engineer CMOS for low temperatures, and why should it provide the benefits? Engineer CMOS, and engineer is such that it has the same IOF, which is the leakage current, at low temperature as it's there in the room temperature. So you have the same leakage current. Now, the subthreshold slope depends on the temperature. As you reduce the temperature, it becomes steeper. As the slope becomes steeper, you can have the lower supply voltage. And I'm going to show you that you can go down to 200 millivolts or so. As a result, your threshold voltage is also lower, and the circuits work, and it is still way above the thermal noise floor, and the circuits continue to work. This all happens because there are two fighting exponents. Mobility increases as temp raised to the power 2.3, and the density of states decreases approximately temp raised to the 1.3. So overall effect is that the transistors become faster with much lower energy, and there is a more than adequate signal to noise ratio. So here is a very simple analysis to show you as to why this happens. On the x-axis, you have the temperature in Kelvin, and the room temperature is where we operate today. And on the y-axis, you have the supply and the threshold voltages as how they scale as you reduce the temperature. So you can have all the way down to something like 100 millivolt supply voltage at very low temperatures. Threshold voltages will scale, and look at the noise floor. The noise floor goes down, way down. So the circuits continue to work at low temperatures. What's the benefit? The benefit is like this. There's a frequency, energy, and power consumption. Frequency increases by 32x. As you reduce the temperature, the total gain is 32x in frequency. That means today's 4 gigahertz design runs at more than 100 gigahertz. The energy reduces by 1000x, and overall power consumption is 50% at 32x the frequency. That means today's 4 gigahertz design at 100 plus gigahertz will consume only about 45 watts. Again, this is just a paper analysis, but something to think about. Let's look at the figure of merit. The figure of merit as defined by energy delay square, that means lower the energy, the better off, lower the delay, you are better, and the figure of merit energy delay square is a voltage invariant metric which goes down by 5 orders of magnitude. Josephson junctions are about 1 picosecond, 1 attojoule. CMOS could also achieve 1 picosecond, 1 attojoule, and that's shown to the left on the relative scale of the figure of merit as you reduce the temperature. So the bottom line is innovative ideas such as CMOS engineered for low temperature can also extend Moore's law in the medium term. Let's switch the gears a little bit and look at the emerging memory technologies. What's out there for the memories? So here, for example, is the SRAM. We are all familiar with 6 transistor SRAM cell, which is a workhorse today for caches and for internal memories, and this is logic integration friendly. Then there is a DRAM, which is our main storage for all our compute system. It's a commodity. The problem for both SRAM and DRAM is that they are volatile. NAND flash. NAND flash is again mainstream. It has a very high density, and the way it operates is you change the threshold voltage of the transistor by having the floating gate. Then you have the emerging memories such as the phase change memory. Phase change memory also has a very high density. It's non-volatile, and it works on the principle of having material which is either amorphous or crystalline, and depending on the material properties you have lower resistance or higher resistance. Then you have something in the research called spin torque memory. A spin torque memory, also known as magnetoresistive memory, works on the principle that the resistance changes is either low or high to encode a 0 or 1 in a memory cell. Ferroelectric memory works on the principle of ferroelectricity, where you have dielectric with the different ferroelectric properties. Magnetic memories, depending on the direction of the magnetic field that is stored in the cell. And finally, the resistive memory, in which case you have the resistance which is either low or high, encoding 0 or a 1. So there are a slew of memories. Some of the memories like the SRAM, DRAM, NAND that are there today being used heavily, and the new ones like the other ones like the spin torque, ferroelectric, magnetic, and resistive. So where do they stand? So here is the landscape of memory technologies. If you look at all these memories, SRAM, DRAM, flash, phase change, spin torque, and so on and so forth. If I look at the size of the memory cell, feature size as measured by feature size of the technology is square, lower is better. SRAM is the largest. DRAM, flash, and PCM are the smallest. Let's look at the array efficiency. Array efficiency is defined by the array area divided by the full chip area. Now you notice that the DRAM, flash, and phase change memory do not have a great array efficiency, and neither do the new emerging memories. SRAM has the highest one. Let's look at the density. SRAM density is not as great, but the DRAM is higher, flash is even higher, and all the new research memories are nowhere close. If you look at the performance as measured by the cycle time for read and write, again SRAM is the fastest, followed by the DRAM, followed by the flash, and all the new memory technologies are nowhere there. Then you can do the same thing for the energy. SRAM is the lowest, followed by the DRAM, and if you look at the endurance, all the new memories have fairly decent endurance, but the flash and phase change have the lowest endurance. This is the lots of data. So let's look at a scorecard. SRAM, DRAM, flash, phase change, all these other memories, followed by the capacity, the performance, all the different attributes that you look for. What you come to the conclusion is that the SRAM is the small and the fastest, so it's here to stay. DRAM is the balanced one. It's got the capacity, speed, and energy, followed by flash and maybe PCM. All the other memories, they have a lot of potential. They should be in the research, but they are not ready yet for the next 5 years. So SRAM, DRAM, and flash, these are the fundamental technologies, maybe PCM, for the next 5 years. And all the other research must continue so that we can use it when it's ready. So how do we extend Moore's law for the near future? For the near future, we really need to start looking at things like, first of all, let's look at how Moore's law we followed over the last several decades. In the 70s, it was doubling the transistors. Then in the 80s, it was doubling the transistor density. Then in the 90s, it was doubling the frequency. Then in the 2000s, it was doubling the performance. In the last decade, it was doubling the transistors for the same dollar. In the future, we really need to start thinking about how do I double the value per dollar that the end user pays for it. That's my proposal. Because if you go back and start looking at the 70s, 80s, 90s, 2000s, what you did was you measured it, but at the end, you double the value that the end user really saw. So what we need to figure out is to how do I measure the value as a metric. And here's an example. Cell phones. In cell phones, you add value each generation with the processor performance, battery life, connectivity, storage, user experience. Putting it all together, you double the end user value for the same dollar cost. And if you do that, then you're following Moore's law. How do we do that? There are lots of enabling technologies, and here are some examples, such as package level integration, multi-chip, 3D integration of memory, storage class memories, advanced battery technologies, communications such as 5G+, and you can go on and on and on at the system level technologies that you can go and exploit to further Moore's law. Let's also start looking at how can we go and regain the efficiency that we are lost in the past. So let's look at the transistor usage in the designs as to how we use them in the past. So here is one example using microarchitecture on the x-axis. You went from simple designs to on-die cache pipeline designs, then to superscalars, then to out of order and speculative, deep pipelining, and then we went back to non-deep pipelining, and you will see why. On the y-axis, you have the increase in die area, integer performance, floating point performance, and especially the energy efficiency. One is the baseline. So what you see here, from one generation to the other, you increase the die area, 4x in the first case to close to 3.2x in the second case. And as you increase that, the die area, your integer performance also increased. Your floating point performance also increased, but your energy efficiency in all the first 4 cases decreased. So essentially what you did was you increase the die area to get a little bit of performance at the expense of reducing your energy efficiency. And we fixed that when we went back to the future, what we call the non-deep pipelines. So performance and productivity is something that was a driving force for transistor usage, but this was all at the expense of efficiency. So what we must do moving forward is reclaim the efficiency through simplicity that we lost in the last several decades. Energy consumption. This is something that has also been overlooked. We always worried about the design that gave you the highest computation. But where is the energy consumption really? Energy consumption is shown over here. All these blue lines are showing the different instructions in this case ARM microprocessor. On the x-axis, you have the energy in picojoule. All these different instructions consume of the order of 100 picojoules or less. Let's look at the energy that's used by the caches. This is for the data movement. The energy in data movement, that means reading an operand from a cache on the chip itself, is 10 times more than what you see than it takes to execute that instruction. If you go outside to the memory, to the DRAM, it's 100 times more. So what we really need to consider is the data movement and go and reclaim the efficiency. So how do we do that? Here, in the near future, I'm suggesting how to extend Moore's law from 1 to 5 years. Number 1, reduce the data movement, because that's where most of the energy is spent. We need to re-architect memory hierarchy, and especially the software stack that comprehends data locality, so that we don't have to move the data far away from where we are processing it. Second thing that you can do is reclaim efficiency which was compromised for productivity, such as by having simpler microarchitectures, thinking about thread level parallelism versus instruction level parallelism. Ask questions like, is virtual memory necessary? Go and figure out what is the cost of a TLB miss, and you'll be amazed that the cost of a TLB miss is a lot more than what you would think it is. especially considering that this involves accessing lots of data from the DRAM. Third, identify the end user value, employ system level technologies, and architect a balanced system to double the value that we provide to the end user. This is all great. Now here is my last slide, which is I'm going to talk about what does it all mean to HPC. So let's spend some time on the HPC landscape as to what extending this Moore's law means to HPC and how HPC has or has not been extending Moore's law. The first graph here shows you the Rmax versus Rpeak of the top 500 rank 1 all the way from 93 to June of this year. What you notice is Rmax to Rpeak is of the order of 72%. That means 72% of the peak performance is delivered to Rmax. And we have been using Rmax as a value metric for the last 3 decades or more. Well, let's look at the Rmax to Rpeak of the top 10 of this year. Again, that's 70%. So it's consistent. It's a consistent metric. Now let's look at the Rmax to Rpeak of different architectures. We have got ARM, you've got GPU, you've got a machine like Sunway, you've got a Xeon and Xeon Phi. I just picked a few representative architectures. And again, what you notice is close to 70% is what you get on Rmax. And if you look at the energy, Rmax energy in terms of picojoule per flop, and you see a huge discrepancy there, but on an average 186 picojoule per flop. The question I'm asking is this the value metric for today's HPC apps? Is this what you think is the end user really looking for? Because if HPCG, if you believe that a metric like HPCG is really the one that represents the final value that the end user is going to get, then the first graph shows that it's only 2.3%. The second graph shows it's maybe 1.5%. The third graph here on HPC, the similar graph, shows again 1.5%. And you can see that energy is 13 nanojoules. 186 picojoule versus 13 nanojoules. Pico to nano, 3 orders of magnitude. And 1.5% on an average, as opposed to 70%. So clearly, there's a 50x difference from the metric that you believe is providing the value versus a realistic metric as to what an end user is expecting. So if you really want to go follow Moore's law, all you have to do is double that percentage, say instead of 2%, 4% of Rpeak to HPCG performance, and that would give you double the Rmax performance or equivalent doubling of Rmax performance. So architect a system for HPCG as an example. That may be a different metric, but even at the expense of Rmax. And if you want to see some detailed discussion, I highly recommend the website extremescale.com/HPC, where there is a lot of discussion on this particular topic. So to make the long story short, here's my summary. Moore's law continues, and the way I would interpret it is 2x the value every 2 years for the same dollar cost. We must continue the device research to replace CMOS in the longer term, need innovative approaches to augment CMOS in the midterm, reclaiming of efficiency in the short term, and there is a call to action to HPC. Reconsider the value and act accordingly. Thank you very much for your attention.